In part 4 of metric space, we will study the definition of adherent point, isolated points, and accumulation point of set. Let us start by the definition of adherent point. Let A is a subset of X. X is a metric space. Let alpha is a point in X set. And if every open sphere about alpha contains a member of A, then alpha is called an adherent point of set A. Adherent point is also called contact point, and the set of all adherent points of set A will be denoted by A bar. Isolated point. If alpha belongs to A and there exists an open sphere about alpha which contains no member of A other than alpha, then alpha is called an isolated point of A. Accumulation point. Let alpha belongs to X and A is a subset of metric space X. If every open sphere about alpha contains a point of A different from alpha, then alpha is called an accumulation point of set A. Accumulation point or limit point of set A. Let us see what is the connection between the accumulation point and adherent point. This is a simple exercise which proves that X is a limit point of A if and only if X is an adherent point of A minus X set. See, if X is a limit point of A, limit point or accumulation point of A, by the definition of accumulation point, we say that a point X is a limit point or accumulation point if every open sphere about X contains a point of A different from X. Symbolically, if you take NXR, an open sphere about point X, then NXR intersection A minus X must be non-empty by the definition of accumulation point of set A. This is true if and only if X is an adherent point of A minus X. Adherent point of A minus X. Because definition of adherent point says that point X will be an adherent point of set if every open sphere about X contains a member of A. So, X is an adherent point of A minus X. Therefore, a point X is a limit point of A if and only if the point X is an adherent point of A minus X. Let us see some important points to remember about this adherent point, isolated point, and accumulation point. First is, every member of A set is an adherent point of A, but the converse is not true. Point 2, every accumulation point of A is an adherent point of A, but the converse is not true. Number 3, every member of A is an isolated point of A, but converse is not true. A bar, which denotes the set of adherent points, is equal to A union AA. Here A superscript A is the set of accumulation points of A. So the set of adherent point is equal to the set A union set of accumulation points of A. Number 2. If A star denotes the set of isolated points of A, AA denotes set of accumulation points of A, then A star, AA are always disjoint. Why they are disjoint? This is very much clear from the definition of disjoint point, from the definition of isolated point and accumulation point. As isolated point is the point of set A if there exists an open sphere about the point which contains no member of A other than alpha. But that accumulation point is a point for about which every open sphere contains a point of A different from the point itself. Therefore, A bar is the disjoint union of A star and AA. That is the disjoint union of isolated points and the accumulation points of set A. Let us prove this by examples. If we take set A is an open interval 0 to 1 which is a subset of real line. In this case, it is easy to see by applying the definition that A star, that is the set of isolated points of A, will be empty, and a set of accumulation points for this set A will be the closed interval 0 to 1. And we know that A bar is the disjoint union of A star and accumulation points. So phi union closed interval 0, 1 will give you closed interval 0, 1. In example 2, if you take set of integers here, A star, that is the isolated point set, is the set of integer itself. Set of integers itself. And please note this, correct it. This is not A bar, this is the set of accumulation points, and set of accumulation point will be an empty set here, and A bar, that is the set of adherent points, is the set Z itself. So A bar is the union of isolated points of set A and accumulation points of set A, which comes out to be the set itself. It is Z. Make a correction here, it is Z. In third example, if A is the set containing point 1, 1 by 2, 1 by 3, 1 by 4 and so on, for this particular example, we see that the set of isolated point is set itself, and set of accumulation point contains only the one point, that is 0, and in fact which is not the member of set A. And A bar, which is the union of set of isolated points and set of accumulation point, it is AA. In some books it is also denoted by A hat. AA and A hat, these are both the notations for accumulation points. So A bar is equal to A star union set of accumulation points of A. Now A bar is called closure of A. We will call A bar as the closure of A. And the set of accumulation points of A is called the derived set of A. These are the terminology of very important terminology in metric space. The set of accumulation points of set A is called the derived set of A. Now this theorem says that let alpha belongs to X. A is a subset of X. X is a metric space. The point alpha is an accumulation point of A if and only if each open sphere about alpha contains infinitely many members of A. To prove this theorem, see, in this sufficient part is just obvious by the definition of accumulation point, and to show the necessary condition of this theorem. Let us suppose an alpha R is an open sphere about point alpha. Let us write alpha as alpha naught, and here the radius of this open sphere R as R naught. Now, by definition, there exists point alpha 1 belonging to this sphere and alpha naught R naught such that alpha 1 belongs to A, but alpha 1 is not equal to alpha naught or alpha. Let us define R1 as rho alpha 1, alpha 2. Rho alpha 1, alpha 2 is the distance of alpha 1 and alpha point. This is the distance of point alpha 1 from alpha. And by the same argument, there exists another point alpha 2 in set A such that alpha 2 is not equal to alpha and alpha 2 belongs to this open sphere and alpha R1. Let us define R2 as the distance of point alpha 2 from point alpha. And similarly, we can find another point alpha 3 in sphere N which centered about alpha with radius R2 such that alpha 3 is a point of A and alpha 3 is not equal to point alpha or alpha naught. Now define R3 as the distance of point alpha 3 from alpha, and proceeding in the same way, we will obtain a sequence of numbers alpha n such that alpha n belongs to the open sphere N centered about alpha with radius Rn minus 1, and where Rn is the distance of point alpha n from point alpha. As we see that the distance of alpha 1 from alpha is less than R0, distance of alpha 2 from alpha is less than R1, distance of alpha 3 from alpha is less than R2, and so on. So this is clear that the radii are going on decreasing. R0 is greater than R1, R1 is greater than R2, R2 is greater than R3, and so on. And further, rho alpha n from alpha is equal to Rn, which is less than Rn minus 1, right? But Rn minus 1 is the rho alpha n minus 1 from alpha, which shows that rho alpha n from alpha is not equal to rho alpha n minus 1 from alpha, which shows that alpha n is not equal to alpha n minus 1 for any n. So this argument shows that for every m not equal to n, we have alpha m not equal to alpha n. Also, n alpha Rn is contained in, it should be contained in. Also, n alpha Rn is contained in n alpha R for every value of n, as alpha n plus 1 belongs to n alpha Rn for every n. So we see that alpha n plus 1 belongs to n alpha Rn for every value of n. So this proves that every open sphere about alpha contains infinitely many members of A. So this proves that point alpha is an accumulation point of A if and only if each open sphere about alpha contains infinitely many members of A. That is it for this part of metric space. Thank you.